A concentration that's used all the time in environmental chemistry and almost never in other areas of chemistry is parts per million, parts per billion, and the like. And although these initially feel kind of awkward, they're really similar to percent. And so when we think about percent, this is just parts per hundred. And when we calculate the parts per hundred, we kind of go back and forth seamlessly between percent and parts per hundred. So if I say that something is 12%, then we know that if we actually want to do a calculation with this number, we're going to use 0.12. And the same thing is true if we're talking about something like parts per million. That if we say that something is 12 parts per million, but we actually want to calculate the amount, like mass of something, then just like we did 12 divided by 100 to get this 0.12, we would do 12 divided by a million in order to get the decimal number that we would multiply by mass, for example. So let's consider a couple of examples using parts per million and interconverting between other concentration units that we might use. For example, let's look at molarity. Molarity is a really familiar one in chemistry. We use it all the time. We know it's moles divided by liters. And so we're used to kind of thinking in molarity and using this as a way to get the mass of a quantity in, the mass of a material in a volume of a substance that we kind of happen to be measuring. So let's apply this to an environmental chemistry perspective, right? If we look at the contaminants that might be in water, copper is one of these, and copper is one of those borderline contaminants where a little tiny bit of copper is not really problematic, but you don't want very much. So in the EPA, our Environmental Protection Agency, we have what are called secondary standards and primary standards, and these usually create a boundary. So the secondary standard is an acceptable amount of stuff that's in the water, even if we might not want it in the water at all. The primary standard is we have to take action now because there's too much. So for copper, the secondary standard happens to be 1 milligram per liter in drinking water. So milligrams per liter is not molarity. It's also not parts per million in this kind of context that we're used to seeing. So that feels awkward. But the good thing about milligrams per liter is that it's pretty easy to convert into molarity. So let's think about it. If we have 1 milligram of copper per 1 liter of drinking water, then we should be able to convert that into moles per liter. First, we're going to remember that there are 1,000 milligrams in a gram. And then we're going to look up the molecular weight of copper. And if we go to our periodic table, we will find that in 1 mole of copper, this will weigh 63.546 grams. So if I cancel out my units, then, my milligrams will cancel, my grams will cancel, and I will be left with moles over liters, which is what I want for molarity. So if I go and do that calculation in my calculator, I'll get 1.6 times 10 to the minus 5 molar copper. And it's really copper, probably copper plus or copper 2 plus. These are the two most common soluble ions of copper. So it wouldn't be copper metal. So, all right, we've gone from milligrams per liter to molarity. So let's figure out how to go to parts per million. So here's where we're going to do a small approximation, but it's going to be an okay one. See, parts per million, when we're talking about these parts, we can talk about a lot of different things. We could talk about atoms or ions. We could talk about molecules or molecular ions. We can talk about mass. We can talk about moles. So there's lots of different parts, and as long as we have the same kind of parts that we're talking about, like the number of atoms of copper in a sample of counted molecules of water, for example, that would be parts per parts. So you can imagine that if we are looking at the number of moles of copper, then we would need to know how many moles of water we have. The other way that we can look about it is we can think about grams of copper in grams of water. Or we can talk about, well, anyway, those are probably the two most common ways that we can think about it. So if we go back to our 1 milligram of copper in 1 liter of water, and it's really 1 liter of solution that includes all of those little particles. But if we think about the density of that water, density is the way that we can convert between mass and volume. So we use rho is equal to mass over volume. And for mass, I'll probably use a small m, but I just didn't want to be confusing. So here's our estimate. Our estimate is that the density of water is approximately 1 gram per milliliter. And although this is an approximation, since we only have 2 significant digits on our milligrams of copper per liter, this 2 significant digits for our density is probably going to be okay. And the density of water is approximately 1 gram per milliliter over a pretty wide range of temperatures that are close to room temperature. So it turns out to be an okay approximation. So if we go ahead and include our grams per milliliter in the water, then we will remember that 1 liter of water is the same as 1,000 milliliters. And so using our density now, and I want to get to parts per parts, so I'm going to go ahead and convert those milligrams back into grams of copper as well. So if I go ahead and do this, then I'm going to have 1 milligram of copper divided by 1 million grams of water. And this is equivalent to 1 part per million copper in the water. So what does that mean? That means that what we just kind of discovered here is that when we talk about milligrams per liter as a unit, this is the same thing as parts per million, excuse me. And at least with an approximately 1 gram per milliliter density for water. So there is an approximation there, but this is pretty convenient because it means that we can use these 2 units pretty much seamlessly. And when we find a table that talks about milligrams per liter, we don't have to be confused. We can automatically in our mind say, oh, that one is parts per million. So let's look at another example. So in water, seawater contains a lot of different dissolved ions. So let's think about calcium. Calcium is probably the most abundant ion in the water after sodium and chloride ion. And if we look up the approximate concentration of calcium in water, it is approximately 400 parts per million. Now, ion concentrations do vary depending on where you are, and so the approximate nature of this is just kind of what we have to deal with. So let's figure out what the approximate molarity is of the calcium in the seawater. And we're interested in calcium in seawater in part because it's necessary for sea living creatures to be able to scavenge calcium from the water in order to build their shells. Now, it's not the only factor for them being able to build shells. The acidity is also important, but there has to be calcium there so that they can create those little shells. So if we're looking at 400 parts per million, this is equivalent to our 400 milligrams per 1 liter. And this is a bit off because the density of seawater isn't exactly 1 milligram per liter, but it's going to be close enough since we're just making an approximation. And if you're interested, the density of seawater is a little bit higher, probably closer to 1.03 grams per milliliter, but this is close enough. So if we go ahead and do this calculation, we can remember that all we're doing to go from parts per million or milligrams per liter to molarity is just to convert the milligrams to grams and then use the molecular weight of the calcium. And those ions they have the same weight because the extra electrons that are gone don't really weigh enough to worry about it. So if we go ahead and run this calculation, we get 0.01 molar calcium. And this is a little bit of a more familiar unit for us to use than parts per million, and it just turns out to be such an even number because the molecular weight of calcium happens to be 40 and we're at 400 milligrams, so this is totally coincidental. But if you feel more comfortable with molarity, you can go ahead and convert the parts per million into molarity in a pretty straightforward way. So when we're working with solutions, we probably will like to use moles per liter instead of parts per million. But the other place that you'll see parts per million and parts per billion is with gases. So with our gases, if we think about ozone, for example, the EPA limit for ozone is 0.1 part per million for 8 hours of exposure doing light work. It matters on what you're doing and how you're breathing and everything. So if we want to know how much ozone there actually is if we're around the 0.1 part per million, well, we have to think about what kind of units we want to go to. So maybe we want to go to, I don't know, an actual quantity, number of moles. So if so, we need to think about a volume, and we need to think about a pressure, and we need to think about a temperature because we're going to use the ideal gas law again. So let's imagine a room that is 10 feet by 10 feet by 10 feet, just for easy numbers. And we'll go ahead and use 20 degrees Celsius and 1 bar of pressure. And so if we think about 0.1 part per million, this is 0.1 0.1 part per million is the same as 0.1 divided by a million. So this fraction would be 1 times 10 to the minus 7. So if we have a 10 by 10 by 10 foot cubic room, and we want to know how many moles of gas are in that room, we need to do some unit conversions. So 10 feet cubed is going to be cubic feet. If we look up cubic feet, 1 cubic foot is the same as 28.3-ish liters. And so the volume of this room is going to be, we'll call it 2.8 times 10 to the 4 liters. And our temperature at 20 degrees plus 273, we always have to convert into Kelvin, is 293 Kelvin. With a pressure of 1 bar, then if our ideal gas law is PV equals nRT, then the number of moles is PV over RT. So plugging in all those numbers, this gets us 1.15 times 10 to the 3 moles of gas. And so now if we multiply that times our parts per million, times 1 times 10 to the minus 7, we're going to get a total of 1.15 times 10 to the minus 4 moles of ozone in the room.